A data transmission under combinational logic circuits. It is the transfer of data over a point-to-point or point-to-multipoint or multipoint-to-point. First is a decoder. It is a logic circuit that converts an n-bit binary input code into a maximum 2 to the n, such that each output line will be activated for only one of the possible combination of inputs. So that is a decoder. Or a decoder is a combinational circuit that converts binary information from n input lines to a maximum of 2 to the n unique output lines. So it is widely used in the computer system. So that is for memory system, then to address the code from the CPU to activate storage location specified by the address code. Also used to convert binary data to a form suitable for displaying on decimal readouts. Can be used to implement combinational circuits, Boolean expression, and etc. So we have the first decoder, the line decoder. So we have 2 by 4 line decoder. It is called 1 4 line decoder. Then we have 3 by 8 line decoder or 4 by 16 line decoder. And we have decoder with enable. So decoders are available in 2 different types of output forms. We have the active high output decoders and the active low output type decoders. So active high output type decoders are constructed with AND gates, and active low output type decoders are constructed with NAND gates. So we begin with our decoder at active high output. So the 2 by 4 line decoder, number of inputs is 2 and number of outputs equals to 4. So input is AB, output will be D3, D2, D1, and D0. If we have 0, 0, it means that we have only D0 equals to 1. If we have 0, 1, that is only D1 equals to 1. And if we have 1, 0, that is only D2 equals to 1. If we have 1, 1, it is D3 equals to 1. If we have to do the circuits, first we have to get the expression for D0, that is 0, 0 for your A and B, so that is A bar, B bar. D1 is E bar, B, then D2 is EB bar, and D3 is EB. So you can see that your D1 belongs to 0, 0, that is E bar, B bar. Your D1 belongs to 0, 1, where B is active, or 1, so that is E bar B. D2 is belong to 1, 0, that is EB bar, and D3 belongs to 1, 1, that is EB. So this is now your logic diagram of this 2 by line decoder, and we have this block diagram. We have 2 inputs and 2 unique outputs from D0 to D3. Then for a 3 by 8 line decoder, input is 3, output is 8. So input is EBC, your output is from D0 to D7 or D7 to D0. If this is your input combination, this will be our output. If we have 0, only D0 is 1. If we have 0, 0, 1, only D1 is 1. If we have 0, 1, 0, only D2 is 1. If we have 0, 1, 1, it is 3. D3 is 1. If we have 1, 0, 0, that is 4. D4 is 1. If we have 1, 0, 1, that is 5. D5 is 1. If we have 1, 1, 0, that is 6. That is D6 is 1. If we have 1, 1, 1, it is equivalent to 7. So D7 is 1. Then we have to get the expression of D0. That is A bar, B bar, C bar, because they belong to 0, 0 for your variable EBC. Then D1 is A bar, B bar, C because it belongs to 0, 0, 1. Then D2 is A bar, B, C bar because it is belong to 0, 1, 0. Then D3 is A bar, B, C because it is 0, 1, 1. D4 is A, B bar, C bar because it belongs to 1, 0, 0. D5 is 1, 0, 1. D6 is 1, 1, 0. And D7 is 1, 1, 1. So this is your logic diagram, and this is your block diagram. So logic diagram has 8 outputs from D0 to D7. In your block diagram, you have also D0 to D7 with 3 inputs. 4 by 16, 4 inputs, 16 output. So we have this combination. So we have 16D from D0 to D15. Every output corresponds to your input combination. If you have D0, it is 000. If you have D1, it is equivalent to 001. If you have D2, it is equivalent to 0010. D3, 1100. D4 is 1011. D5 is 1010, and so on. So you have to draw your circuits. So this is your 4 by line decoder. We have 16 output, 4 input lines, and your block diagram also has 16 outputs with 4 input lines. We have also decoder with enable. So we have 2 by 4 line decoder. Number of inputs is 2, but we have another input which is the enable. Then the same output is 4. So this is our truth table. We have EB as our inputs, but we have an enable input. We call this one as E. You have your output. So this is your truth table. If your enable is equivalent to 0, if your E and B is either 0 or 1, all your output must be 0. If your enable is equals to 1 and your input equals to 0, then your decoder will operate or will function as a decoder. So this is D0 equals to 1 because your input is 0. If your input is 01 and enable is 1, then that is D1. If you have 10, this is equivalent to 2, so D2 is 1. If you have 1, that is equivalent to 3, then D3 is 1. If your enable is equals to 1. But if it is 0, it's either your input 0 or 1. Your output are all 0. So we have this expression for your D0, expression for your D1, expression for your D2, and for your D3. So this is your circuit. And this is your logic diagram. So in your decoder with enable in a block diagram, we have your enable in your lower side and your input in the left side, and the right side will be your output. That is also for your 3 by 8 line decoder. For input, because we have one enable. So we have output is 8. We have EBC, we have 4 inputs, one of which is an enable. Then we have this one, your output from D0 to D7. So this is your truth table. If we have an enable which is equivalent to 0, if your input is either 0 or 1, your output must be all 0. If your enable is equals to 1, then your decoder will function as a decoder. If we have 0, that is this 0 is 1. If you have 001, then that is D1. If you have 010, that is D2. If you have 011, that is D3. 100, D4. 101, D5. 110 is D6. And 111 is D7. Then we have to get the expression for D0, for D1, D2, D3, D4, D5, D6, and D7. You have to draw your logic diagram and your block diagram. So the logic diagram, we have your enable in your outer side. Then this is our input EBC. This is our output using an AND gate. For your block diagram, we have your input in your left side, output in your right side. Your enable is your bottom side. Then for decoder with a low output with enable. So 3 by 8. So number of inputs 4, one of each is the enable. Output is 8. So we have E, B, C. Then our output is D0 to D7. So this is now your active low output. If you see active low, it means that when your input is 0, 0, that's belong to D0. So D0 must be equivalent to 0 because it is active low. If you have 0, 0, 1, then D1 is 0. If you have 0, 1, 0, that is 2, D2 is 0. If you have 0, 1, 1, D3 is 0. Then if you have 1, 1, that is D7 is 0. This is only when your E or your enable equals to 1. But if your enable equals to 0, it's either your input is 0 or 1. You have an output is equivalent to 1. So, for D0 expression, D1 expression, D2 expression, D3 expression, that is our D4, D5 expression, D6 expression, D7 expression. So for your circuit, will be this one, using your NAND gate. So your NAND gate using an inverter, so we have this output. So this is your block diagram. We have 3 inputs and 8 outputs with a bubble to represent that is a low active decoder. So for an IC, a low active decoder with a 3 by 8 is called a 74138. This is the logic diagram, and this is the block diagram of your IC. There are 3 enables in your 138. You have E3, E2, and E1. E3 is active high, E2 and E1 is active low. So it should be connected to ground if we have to use this one as a decoder. And this one must be connected to high, your E3. Another one is 154 or 74. 154, that is a 4 by 16 decoder. So this is the pin configuration of your 4 by 16. Your block diagram of your 4 by 16. You have to enable E1 and E2 and they are all active low. So decoder can be used to implement a combinational circuits or Boolean explain function. Example, if we have to implement a full adder using decoder and OR gate. So full adder, we have this truth table, we have this expression, a symbolic expression in terms of your sum, where you have a 1, at 2, at 4, and at 7. And your carry in the symbolic expression, we have a 1 at 3, at 5, at 6, and 7. So, since we have 3 variables in your input, so we have to use a 3 by 8 decoder. So since we have a summation for your sum at 1, 2, 4, and 7, so we have 1, D1, D2, D4, and D7 all together to have your sum because it is a summation sign. For your carry, we have 3, we have 5, 6, and 7 all together to have a carry for your summation sign for your carry. So for your implementation of your comparator 2 by 2, so this is the truth table of our comparator. So we have to get the symbolic symbol for your equal, greater than, and less than. So symbol for your equal, that is 0, 5, we have 10, and 15. For your greater than, we have a symbolic symbol of 4, we have 4, we have your 8, 9, this is your 12, 13, and 14. So this is greater than. So this is greater than and this is less than. So remember this is less than. For less than, we have 1, we have 2 and 3, followed by 6 and 7, and your 11. So this is now your circuit. So just get the equation of the two 0, 5, 10, and 15, 4, 8, 9, 12, 15, 13, and 14. Then for your less than, you have 1, 2, 3, 6, 7, and 11. So we have to use 4 by 16 because we have 4 variables in our input and it has 8 output combination from D0 to D15. So we have to realize a 3 by 8 decoder using 2 by 2 by 4 decoder with enable. So it means that if you are going to buy a 3 by 8 but in the market there is no available 3 by 8 but there are only 2 by 4 decoder with enable. So we have to use this 2 by 4 decoder with enable to construct a 3 by 8 decoder. So this is a truth table of your 3 by 8. So if you have an input ABC, your output is from D0 to D7. The truth table of your 2 by 4 with enable is this one. So if enable is 0, then your decoder will not function as a decoder. If it is equals to 1, then it will function as a decoder. So we have to construct chip 1. So we have your input A, B, C. We have A, we have B, and C. So that is our IC number 1 using this output. So if it is 0, then you have 0, 0, 1. Then this is your output. That is your EBC. Next, your chip number 2. That is D0 to D3. Then we have your combination from 1, 0, 0 to 1, 1, 1. If it is 1, this is 1, 1, 1. And all others are 0. So it means that in your chip 1, we have your enable as 0. It will function your IC number 1. If your enable equivalent to 0, your IC number 2 will not function as decoder. If your enable equals to 1, your IC number 2 will function as a decoder, and your IC number 1, it will not function as a decoder. So, you have your input EB from your decoder, this one EB. Then we have your E as your enable. Then E is connected to B and B is connected to C. So it means that your EB is your B and C, and your enable will be your E in your 3 by 8 truth table. So this is your truth table for your 2 by 4. If we have to use a 2 by 4, so that's why we use the input variables E, B, C, B, and C for this one for your 3 by 8, and E is our enable from your 2 by 4. So we have B and C connected with EB, and your enable connected with your enable in each of your 2 by 4. So if this is equals to 0, only your IC number 1 will function as a decoder. This decoder number 2 will not function as a decoder. It will have an output of all 0. If your enable is equivalent to 1, Your decoder 2 or your IC number 2, this one, will function as a decoder because it is equals to 1. Then this output will determine what is your input combination. But your IC number 1 is, since it is equals to 1, using an inverter, then it is equals to 0. Output for this one are all 0. So this is your 3 by 8 decoder using 2 by 4 decoder with enable. For encoder, a decoder identifies a particular code present at the input terminals of the circuits. So the inverse of that is the process called encoding. So it is a digital function that produces a reverse operation from that of a decoder. So an encoder has a number of 2 to the n, one and only one of which is in the high state or active, and n-bit code is generated upon which of the inputs is excited. So this is an example of your encoder. If you have to press S0, so this one. If you have to press this 1, 2, switch is on, they are not connected with your output, so they are all 0. If you have to press 1, 2 on, then we have an output of 0, 0, 0, and 1. If you have to press S9 to on, we have an output of 1, 0, 0, 0, 1. If you have, remember, if you have that is 0, if you have to press S0, this is 0, 0, 0, and 0. So that is what you call your encoder. From a readable, human readable data, it will be converted into a binary data. Then we have a decoder with enable will be used as a demultiplexer. So this is our decoder with enable. We can use this one. So this is our equivalent logic gates. We can use that. And opposite, our enable will be our input and our input will be our selector. So this is your logic circuits for your demultiplexer. So remember, in the first slide, we have a decoder with enable. This is your input A and B. We have your enable output is 4, and this is your logic gates. Logic gates of your combinational circuits. We have E and B, and we have your enable. If we have to use this decoder as a multiplexer, we have just to convert your input as a selector and your enable as your input. So before, this is your input and this is your enable. This now is your selector and this is our input. So the multiplexer is a logical circuit that takes a single input source and send it to one of the several 2 to the n possible output lines. So we have one input and we have 4 possible output lines if we have 2 selectors. And it is also called a data router because we have to route your data to a different types of output. So DMUX with 4 outputs, it has 2 selectors. A DMUX with 8 output, it has 3 selectors. So a multiplexer also is a device that selects one of the several input signals. It's either analog or digital and forwards the selected input signal into a single output line. A multiplexer of 2 to the n has an n selected lines which are used to select which input line to be sent to the output. So this is your logic circuits of your demultiplexer. We have multiple inputs and a single output and your selector. To determine the number of your inputs is through your selectors. If you have 2 selectors, it means you have 2 or 4 inputs. If you have 3 selectors, it means you have 8 inputs. So this is your block diagram. So multiplexer is also called data selector. The multiplexer can be used for the implementation of Boolean function or combinational circuits. They can also use for parallel and serial conversion. So we can use MUX or multiplexer to implement a full adder. So remember a full adder truth table, we have 3 inputs and 2 outputs, that is sum and carry. So for the solution, from your input variables, we have to choose one variable as our input for your MUX, and the remaining variables will be our MUX selectors. The size of your MUX will depend on the number of variables remaining as selectors. If there are 2 selectors, then we have to use 4 by 1. If there are 3 selectors, then we have to use 8 by 1. And there are 4 selectors, then we have to use 16 by 1. So for this example, we have input variable A, B, and C. We have to choose one variable as our input, and the remaining variable will be our selectors. If we have to choose C, then A and B will become our selector A and selector B. If we have to choose B, then A and C become your SE and SB. If we have to choose selector A, then B and C will be your SE and SB. So for this one, if we have to choose C, therefore E and B will be our selector is E and SB. So for that selector, we have 0, 0, that is for I0, 0, 0, that is I0, this is 0, 1, that is I1, 0, 1, I1, this is I2, I2, this is I3, and I3. Since with SE and SB as our selector, so we have to use a 4 by 1 multiplexer. So in a 4 by 1 multiplexer, we have also a map method. So we have your input at the upper side. We choose SE and SB as your selector. So this will select your input. Our input is from I0 up to I3. So we have I0, I1, I2, I3. And for your left side, that will be our input for your MUX, which is your C. C can either be 0 or 1. So if C is 0 or 1, this is your pattern. This is 0, 0, so we have 0. You have 0, 0, 1, this is 1. You have 0, 1, 0, this is 2. We have 0, 1, 1, that is 3. If this is your 2, that is 1, 0, 0, that is 4. 1, 0, 1, that is 5. This is your 3. I3, that is 1, 1. 0 is 6. 1, 1, 1 is 7. Next, for the output sum, we have just to encircle where your sum equals to 1. So you have a sum at 1, at 2, at 4, and at 7. Then we have to get the expression based on your circled number. So you circle 1, which belong to C. You circle 2, which belong to C bar. 4, which belong to C bar. And 7, which belong to C. So for output carry, the same. We have I0, I1, I2, I3. So the pattern is 0, 1, 2, 3, 4, 5, 6, 7. So we encircle 3 because we have 3. We have 5, 6, and 7. So encircle 3, that is C bar. 4 and 5, that is C bar or C, that is equivalent to 1. And 7, that is belong to C, we have C. Then, this is now your circuits using MUX. For sum, we have the sum, we have SE and SB, that is A and B. Your input is C. For I/O, it is connected with C as well as I3 is connected with C. For I1 and I3 is connected with C bar, so we have to use a inverter. Then for your carry, your IO is connected with 0 and your I2 is connected with 1. For your I1 is connected with C bar and your I3 is connected with your C. All your selector must be connected with your E and B. So this is the implementation of your pole adder using multiplexer. And that's all for our data transmission.